Now the time has arrived for the most anticipated talk of Rasyanam. We have with ourselves one of the most brilliant minds in the field of chemistry, one of the most decorated professors of our country. He's won numerous awards and honors across the globe, recipient of our country's most coveted award in the field of science, the S.S. Bhatnagar Award. He did his master's from IIT Kanpur, followed by his PhD from Columbia University, New York. He did his postdoctoral research from University of California, Berkeley. Currently, he is a professor at Indian Institute of Science, Bangalore. It is our honor to invite Professor Uday Maitra on the stage to share his wisdom with us through his scintillating lecture. We welcome him with a big round of applause.
Thank you very much for the introduction. Thank you very much for the invitation to come here and share with you some excitements in chemistry. Normally, I wear a periodic table tie for this purpose, for these lectures, for two reasons. I'll mention that in a few minutes. But I thought that in such hot weather, if I wear a tie, I may actually look like a clown. Okay. And so I decided not to do that. But then this t-shirt that I'm wearing, it was designed for an open day in our campus, IISc campus. As you can see, it says open day. That was held Saturday 2 weeks ago. I couldn't be there, but I was gifted this t-shirt. And I thought I will wear this. And not only that, I will also wear this cap, which shows our logo. And interestingly, you see something here. This is the RSC logo because RSC also supported our event. And it so turns out that I have the ACS logo on this side. And many of the chemicals that I'm going to use came from Merck. Alright, so I would like to acknowledge them. They also supported our open day by providing many chemicals. And if you allow me, I will remove this cap because I'm not used to wearing a cap like this. Okay? Alright. What am I supposed to do? Okay. So first thing to do is to switch on my timer. You see that I have 90 minutes put on here. I will take 90 black minutes and a few red minutes, and you will figure out what it means. Now, you know what this means. Not many of you may know because this object in the background, most of you may not be familiar with that. So somebody told me that you need to update your slides, so I updated. Right? So now it looks like a smartphone, and smartphone should not be used, as I was also guilty of putting my smartphone in my pocket. Okay, so let it be away from my microphone. All right. Do any of you know where this picture was taken? You will not know. It's not Mount Everest. Okay? Alright. So this is the name of the place. So you can guess where it could be. Can you recognize this language? It's Russia. Okay? So this is in the southern part of Russia. Alright. So before I begin, I would like to thank Deepankar Bhomik, who helped me bring some chemicals from Bangalore. I would like to thank profusely Dr. Shivapriya and her entire group, in particular Jamina and Sri Madhavi, who are here on the stage to help me with the experiment. So can you please come? So give a big round of applause to Jamina on your left, on your right, and Sri Madhavi on your left. Alright, so Jamina, you need to put on the safety glasses when we do the experiments. Okay, every day in the year is an important day for one reason or other. Okay, it turns out today is also an important day in the history of science. And as you can see, Fisher, this is not the Emil Fisher which some of you know. This Edmund Fisher, he was born on this day in 1920. And he worked on protein phosphorylation and its role on biological recognition, got the Nobel Prize in Medicine in 1992. Fyodor Lenin, he worked on the biosynthesis of cholesterol. You know that many people suffer from high cholesterol and take medicines collectively called as statins. Okay, and that stops the biosynthesis of cholesterol. So it's very important that we know how cholesterol is synthesized in your liver. Okay. So he got the Nobel Prize in Medicine in 1916. There are a class of reactions which are called oscillating chemical reactions, and that was discovered by Richard Noyce, who was born again on this day in 1919. Teflon, which many of you are familiar with, was accidentally discovered on this day by Roy Plunkett in 1938. And last but certainly not the least, James Watson was born on this day. Is it anybody's birthday today, April 6th? Alright, even if it is not, we would like to celebrate something along with this gentleman, Mendeleev, right? You can recognize. And this year has been declared as the International Year of the Periodic Table by the United Nations because the best form of periodic table published by Mendeleev, which is shown here, was published exactly 150 years ago. So this year marks the 150th year of Mendeleev's modern periodic table. Okay. So this was a modern periodic table in 1869. So to celebrate this, let us burst a few balloons. Alright? Shall we do it again? Okay. Normally I do it in real life, but since it's an air-conditioned space, it's a big space. Actually, I could have planned it, but there were some accidents involving hydrogen in our campus some months ago, and I decided to stay away from bursting real hydrogen balloons. Okay. Before we start with the experiments, I would like to emphasize something that is very important when you study any branch of science. Everything, in fact, most so about science. And that is the importance of asking questions. You know, what happens in our high school is that, unfortunately, students prepare for competitive exams. They go to various coaching classes. I'm sure that many of you have gone through this. And my joke is that often in coaching classes, all they teach is how to find 3 wrong answers. Okay? Sometimes the students actually do not learn what the correct answers are. And therefore, it's very unfortunate that those who go to coaching classes and, in fact, get through very competitive exams, they do not really ask questions. But it's very important to do well in science to ask questions. Okay? Let me give you an example. This gentleman has made this statement. You may also recall that when you were very young, maybe 9 to 12 years old, when you come back from school, whoever is at home, maybe your mother, maybe your grandparents, they would normally ask you, what have you studied in the school today? Isn't it? We always do that. But this guy said, the gentleman said, that not my mother. My mother would ask, did you ask a good question today? And then he goes on to say that difference, asking good questions, made him become a scientist. You may not recognize who he is, but his name is I. Rabi, who was a professor of physics in Columbia University, and he got the Nobel Prize in 1944 for discovering a method by which magnetic properties of nuclei could be determined. Okay? And this technique eventually became known as nuclear magnetic resonance. Some of you may have studied NMR, and you probably also know the MRI technique, which is used in medicine. So it was a technique discovered by a physicist, used extensively by chemists and biochemists, still being used, and now, you know, a subset of these experiments are being used by medical doctors. So, I am going to ask you some questions. There is no credit in answering this question, okay? Because all of you have studied this in your history book. But then, I'll show you another picture which looks very similar. What does it have to do with our this particular tower, it's actually a chemical reactor, about which you have studied right from your high school days. Okay? A very important reaction had taken place inside this tower for 55 years, and then the company which used this tower kept it outside their factory as a monument. Okay? You may not know what it is, but you wait till the end to find the answer to this question. Okay? Any guess? Sorry? Louder? Something you have studied in high school. Okay? Alright, and it's very important for the human well-being. Alright. Now here is something that came from the back side of a package of bread. Okay, which many of us eat for breakfast. It's very important that when you buy a package, particularly perishable item, you read what do you read? The expiry date, right? But these days it's also important that you look at what is in there. And sometimes you will find some numbers given there. In fact, if I pick up this bottle of Sprite, again it's on the back side in a label, all the composition is typically given. And here you will see a lot of numbers. These numbers refer to approved food additives, and there are probably thousands of them. Okay, and here some numbers are given: 282, 510, 1100, 260, 300, and so on. Do any of you know what these numbers mean? Do you know what you are taking, what you are eating? As science students in general, and as chemistry students in particular, I think you should pay some attention to these, because you should know what is going inside your body. Of course, these are all approved food additives, but let me list them out. Okay, these are typically called the E numbers. And if I look at these numbers, 282 is calcium propionate, 510 is ammonium chloride, 1100 is amylase. This is used for making the action of yeast better. Then acetic acid, which is commonly called the acidity regulator. Monocalcium phosphate, again acidity regulator. Then E471 is mono and diglycerides. E300 is ascorbic acid, and so on and so forth. So I think it's important that when you buy something, you look at the label and try to understand what's in there, and you can learn a lot of new chemistry about it. Okay. Since it's the International Year of the Periodic Table, I would like to highlight to you a website called isotopesmatter.com. This was a website that was launched by the IUPAC in 2016, and this includes all the elements that are known so far. And how many are there? Not just these many. 180. And 118, all of them have been named now. And you can look at not only the properties of these elements, but also the properties of their isotopes and what are the uses of many of the isotopes. Okay? For example, this is one screenshot from the website, and it says that basically, why do I need to know about isotopes? What information isotopic study can provide to you? Okay? I will not go into any of these details, but I would advise you, and I will strongly encourage you, to look at this website and read on your own. Okay, chemistry often looks like magic. Right? Many of you have thought that I'm going to do a magic show, right? But there is no magic here. It's all science. It's all chemistry. Okay, it will look like magic. Okay, all right. So now what I would like to do. I would like to show you something which would look like magic, but unlike magicians who will never tell you what's happening, most magicians make use of principles of physics and chemistry, but they would normally not tell you why certain things are happening the way they're happening. But I will explain everything. First, the magic, alright? Because we have a very young participant in the first row, and I must do a magic for her, and then the science will come later. So, magic for you. I'm I'm looking for 2 volunteers. Can you get them? Okay. No matter which experiment I'm doing, it's very important that we do things safely. Okay. And I'm going to do a very simple experiment. Okay. But I would like you to put the glove on your left hand and you on your right hand. Okay. But I can assure you that this is a very safe experiment. But when you are doing experiments, you need to protect your eyes. That's number one. First thing you should do in a chemistry lab is to put on safety goggles. In fact, I also encourage cooks in the kitchen to wear safety goggles before they put the chalk on the dal. Okay. Alright, so if I were a magician, I would say nothing is written here. Okay? But that's actually not true. Something is written. Can you hold it on your right hand? And you hold it on your left hand. Left hand. And that's why I have this. Can all of you see it? Move it up as much as you can. So, nothing is written, but something is written. And I'm going to spray a brownish liquid on it. Okay? And magic. Alright? So, let's see how it works out. It's completely harmless. Okay? But you are protected. Right? Okay, very simple experiment. One liquid, 2 different colors. Okay, in principle you can do it in multiple ways. But thank you for your participation. You can remove your gloves and your eyeglasses and go back. You're from which place? Yes. Thank you. Thank you very much. So, chemistry is fun. But the fun part is now over. Now we need to learn the chemistry part. Right? So, any guess? Not from the teachers. Suppose I say this is perchloride. I think it says perchloride. If this is perchloride, what are the 2 different colors? You know, one came as maroon and one color was blue. Right? Now, this is all high school chemistry. The one, and let's see the chemistry part here. The one which turned blue was written with potassium ferrocyanide, which is more or less colorless. But upon reaction with iron chloride, it forms Prussian blue. Right? Whereas potassium thiocyanate reacts with perchloride to produce this blood red complex. Okay? FeNCsH2O5 2+. That's why I got 2 different colors by mixing perchloride. Okay? And you can think about doing other combinations of transition metal chemistry to generate more colors. Okay? There are various versions by which you can do this magic writing. Okay, but this is a very simple one which gives 2 colors with 1 spray. Okay. All right. Since we were talking about isotopes, let's do an experiment with isotopes. Okay, and in particular, the most common isotope that you have heard about is D2O, right? Isotopically enriched molecule. So D2O is deuterium oxide. It's known by another common name. What's it? Right? Heavy water. So do you know why is it called heavy water? Yeah, but it's called heavy water because its density is more. Okay. By the way, heavy water is not healthy water. Okay. Because this particular slide shows you what you see is a tobacco plant grown in 100% water and progressively increasing amounts of D2O. 30, 50, 60 and 70% D2O. So which clearly shows that the growth is significantly retarded when you add D2O. Okay. And since it's a very general audience with different age groups, I will simply say this is because of a phenomenon generally known as kinetic isotope effect. Anything in which you put a heavier isotope any bond in which a substitute a lighter isotope by a heavier isotope will generally lead to a reduction in the rate. And since the human body or the biological system has evolved over hundreds of millions of years using H2O and not D2O, everything is optimized for use in H2O. Okay, and therefore, if somebody offers you a glass of heavy water, then you say thank you, but no thank you. Okay, all right. Now this is the reason why H2 is called heavy water. I mean D2O is called heavy water, right? And you also notice its boiling point is marginally above water. Freezing point is significantly above water, almost 4 degrees. All right. Now let me ask you the second question. What was the first question? About the tower. All right. Think about it. The second question I'm going to ask you is that if I give you 3 ml of D2O, it's expensive. 3 ml of D2O is about 200 rupees. And I will give you another 12 rupees to buy whatever you want. Can you think of a simple experiment by which you can demonstrate in a hall like this that D2O is heavier than H2O? I give you only 3 ml, it is less than 1 teaspoonful of water, D2O. I give you 12 rupees plus whatever you see here or in the chemistry lab. You have to show an experiment right here so that even the person sitting on the last row will be able to see that D2O is heavier than H2O. If you add soap, both water and D2O will form, lather. And also 3 ml of D2O. The fellow in the last row will be updating his Facebook and all that, saying that somebody on the stage is making some soap and something and all that, but they won't be able to see. Think about it, okay? I will come back and do the experiment, but if you have any better idea, I will appreciate that. Okay, one simple question about organic chemistry, okay? And this has to do with chirality and handedness. Okay? And you all know that a carbon atom, a tetrahedral carbon atom, or a carbon atom having so-called sp3 hybridization, if they have 4 different substituents, you get chirality, right? Now, when stereochemistry is taught in colleges, somehow organic molecules and inorganic molecules are treated separately. But if you really think about this phosphorus compound, this pentavalent phosphorus, is it chiral if 1, 2, 3, 4 and 5 are all different substituents? Is it a chiral molecule? Does it have overlap with its mirror image? Think about it, okay? Again, let me throw that to you as a problem. Okay, I will also ask you another question. If I interchange any 2 of these substituents, I with bromine or I with Cl, what do I get? You get the enantiomer, the mirror image molecules, right? If I do the same thing on the phosphorus, interchange 1 and 4, let's say, or 1 and 2, or 2 and 3, is the relationship similar? Think about it. Okay? Again, I will come back to this. This is my third question. But one of the things that you perhaps know is that when you have like the right hand and the left hand, they are mirror images, but they do not overlap. Okay? They are otherwise identical. At least when you are born, you have equal ability to use your left hand and right hand. You didn't know that, but you should have. Okay? But the only way the difference, you can experience the difference is when you interact a right hand and a right hand, or a right hand with a left hand. You try to shake hands with a friend, right? Your right hand and his or her left hand, and you will find that the handshake is not matching. Okay, and that is because when chiral objects interact with another chiral object, they show difference in their properties. For example, here are 2 molecules, okay, and this is called R-limonene and this is S-limonene. They are mirror images, non-superimposable. They are found in different natural products, but they have different properties. They have identical physical properties, except in their optical rotation. But they have different properties in the sense that one smells like orange, this smells like turpentine. I will show you another example of very similar molecule. This is called carbone. The R carbone smells like mint, pudina. S carbone smells like jeera, the small jeera which is used for making pulao and biryani. Okay. Now, in textbooks, you have to see to believe it. Okay. But I somehow feel that you should smell to believe it. Okay. And I have these two samples of R carbone and left carbone, and I will request Srimadhavi to pass it on to the audience. You hold this R in your right hand, smell it. It should smell like pudina or mint with the right hand, and smell it. Pudina-like smell, right? And this was a jeera-like smell. These are mirror images. Boiling points, melting points, everything are identical. Okay, so you can pass it on to the audience and let them also smell the two different enantiomers. And I feel that, in addition to writing in the book, if your teacher can give you samples so that you can smell, you will have a better appreciation for chiral molecules. Now, speaking of chiral molecules, suppose I ask you to bring a chirally pure chiral molecule from home. What would you bring? Suppose the teacher says, please bring a pure chiral substance from your home. You are close, but not quite. Sugar. See, the glucose or glucon D or many other varieties, what you get in the package, they are not pure substance. They have many other things mixed with it. If you dissolve it in water, you will see that it doesn't dissolve in water completely. Okay, because it's got many fillers, some stabilizers and things like that. But cane sugar is 99.8% pure. So that's the pure chiral substance that you can get from home. Okay, so I would like to then start with this experiment. Any thoughts about this isotope experiment? Can you? I think. Oh, if we add salt, both will dissolve. Let me ask you another question before I actually show the experiment. Let me see whether my samples are doing. Yeah, that will be fine. Ice floats on water. Does it give you a hint? D2 ice will float on D2O. But what about D2 ice in H2O? Because D2 ice in H2O should stink. Because ice is 8% lighter than water. So D2 ice will also be approximately 8% lighter than D2O. On the other hand, D2O is about 10.5% heavier than H2O. And what that implies is that D2O ice should be heavier than H2O. And we'll do this experiment here, and lights may be on. And here is what I call a poor man's deep freezer. Okay, I have a sample of H2O and D2O in these two specially cut syringes, and not everything survived during my trip from Bangalore to Ahmedabad via Delhi, but these two did survive. And what did I do with the 12 rupees is to buy food colors. Okay, and so what I have in these syringes is my students, they always play a trick on me. Okay, they don't label these two samples. Okay, so I have no idea which one is H2O, which one is D2O, which in fact is actually good. Because only by doing an experiment, certain experiments, certain things you can find out only by doing the experiment. Okay, particularly if you are doing it for the first time. You can see this looks like orange, and this has this food color, orange food color, which is often used in biryani. And this is green food color, which is often used in spinach, particularly in the summer months when spinach is not very easily available. So to make it look like spinach, you can use, but these are all approved colors. Okay, so what I have is 3 ml of H2O or D2O. One of them is H2O, one of them is D2O, and these are kept frozen in what I mentioned is the poor man's deep freezer, which is nothing but ice and salt. Okay, which can go to a temperature of minus 18 degrees. Okay, so these two samples are there. And then what I'm going to do is to take some distilled water ice. Thank you very much for getting this distilled water ice, and make some water which is really cold. And I will tell you why I'm using ice cold water for this experiment. Okay, so let us have this ice cold water. And now I have with me one ice which is green in color, one ice which is orange in color. Okay, and one of them will float, one of them should. I won't say will, it should sink based on what we have just learned. Okay, so let me make this ice cold water here. And the reason I am using ice cold water is because I mentioned that D2O ice will melt at 4 degrees. Right? So therefore, you will find out that the ice which sinks will actually melt slower than the ice that floats. And that will also indirectly tell you that they are different melting points. Okay? So here is now the ice cold water, and I would like to have one of my assistants to come here and help me with the experiment. Safety goggles first. Gloves may not be needed because this is after H2O and D2O. So since I don't know which one is which, let me try with the green ice first. Okay. And what you do is to have for this one like this and hold it against this like this. Okay. Hold it at the bottom. Okay. And I'm going to dump this green ice and see what happens. This is again a very high-tech $1 million gadget, okay, which I use to drop the ice. Are we ready? Oh, it's really frozen hard. It's not coming out. I need to melt it a little bit. And because it has higher freezing point, it can freeze very easily in ice-salt mixture. Okay, so it should be softened now, and let's see what happens. Very happily, it dropped to the bottom. You could see it, all of you could see it, right? And therefore, that very clearly says that this is D2O. Then hold it again. I will now take the other ice, and again use my $1 million device to let it spill in, and now you see happily the experiment is successful. One floats, one sinks. Thank you very much. And the one which is floating, I push it, make sure that it's not floating by chance, it is indeed floating. Okay, and the other one it has sunk. So what will happen in the next few minutes, you will observe is that the orange ice will melt much faster because this is at a temperature, the water is at a temperature close to its freezing point, whereas the water is below the freezing point of the green ice. Okay, and so this will disappear faster than the green ice, that's number one. And the other thing that will happen is that once the green ice starts to melt, it will produce D2O. Okay, and then the remaining part of the green ice, it will actually start floating on the green liquid. So that is also something you will observe if I remember to show it to you in about 5 minutes time. Okay, alright. So here is one simple experiment with D2 and H2O that everybody can see. Here, sometimes people tell me that, well, if you measure the density of D2 and H2O, that is, you take out 1 ml of H2O, the weight will be 1 gram. You take out 1 ml of D2O, the weight will be 1.1 gram. That will tell you that it's heavier than water. But you know, that's a bad experiment. Okay, because I can measure the weight with the balance over here. But again, the people sitting in the back row will not see what's happening. But on the other hand, this experiment, you know, everybody can see, even in a large classroom, what's happening. And then the ice really, literally sank to the bottom rather rapidly. Okay, okay, so let's see what's next. So this is actually a picture. And this is another experiment done with a much larger piece of D2O ice, and you can see it happily floating on the D2O, which has been produced by melting part of the ice here. Okay, what's the relevance of this elephant here? So, our youngest participant, what shall we do with the elephant? The elephant has dirty teeth. Elephant's tusks are dirty. So we need to make a toothpaste for the elephant. Okay, so some of you must have seen this experiment, which is called elephant toothpaste experiment. Actually, this is an experiment on catalysis. Okay, and the catalysis experiment is the following: H2O2 has a weak OO bond. Okay, we'll come back to the bonding a little bit later. But it has got a weak OO bond, which means it is thermodynamically unstable. But like many unstable molecules, it is kinetically stable. So I have, for example, H2O2 here is not decomposing. So it's happily staying okay. But you shouldn't go too easy on that. But there are certain species which act as catalysts. For example, if I add sodium iodide to hydrogen peroxide, it produces water and oxygen very rapidly. Okay? So iodide acts as a catalyst. But then if I add sodium iodide, how do I know that sodium iodide is the catalyst? Sodium or iodide? I don't know, because sodium ion can also be the catalyst. Right? So to prove that iodide is the catalyst, I'm going to add sodium bicarbonate also. Okay? If sodium bicarbonate does not act as a catalyst, then it will imply that sodium is not a catalyst, and therefore if sodium iodide is the catalyst, iodide must be the catalyst. Okay, so that's the logical thing. And to make things go a little bit better, I'm going to mix some liquid soap with the hydrogen peroxide so that when the oxygen comes out, it will come out as a foam out of this, and it will look like a toothpaste, fit for the elephant. Okay? Alright, so the first thing to do is to take this hydrogen peroxide. I assume this is hydrogen peroxide. The label says hydrogen peroxide, so I believe that. Okay? I will tell you a joke about hydrogen peroxide. Okay? After I finish that. Alright, and then I'm going to add some liquid soap into it. I will not show which brand it is because I'm not promoting any brand. I add some liquid soap, any brand will do, but this should be undiluted liquid soap. There are many YouTube videos on this experiment. Some of them are real, some of them are fake. So do not believe in what you see on the internet all that much. Internet is very useful, but not all of it is real. Okay? So I mix it well and pour it in this measuring cylinder. About total of about 50 ml in a 100 ml measuring cylinder. Now just a warning to those who are going to clean it up later. This is 30% hydrogen peroxide, so be careful while cleaning because it can corrode your skin. Okay, the first part of the experiment is to add some sodium bicarbonate. I add some sodium bicarbonate, and to confirm that sodium indeed is not the catalyst. Okay? Now, so anything happened other than a little bit of foam due to my shaking? Nothing happened. Okay? So now I'm going to add some salt, sodium iodide. Can I get one more conical flask here? Not immediately, but a little bit later. So I take sodium iodide. I put too much of it, but it doesn't matter. And dissolve it in a little bit of water. Are we ready? Can you all see this? So this is soap, hydrogen peroxide, and now I'm adding sodium iodide. Okay, I need to be careful because, and here comes the toothpaste. Okay, you can see that the rate is extremely fast and the foam is coming out rather speedily. Okay, and that's why we have this protective tray over here. You see a little bit of steam coming out. This experiment is actually quite harmless because hydrogen peroxide may be very reactive, but we are producing only, what are we producing? Oxygen and water. Okay, and a little bit of heat, which is okay. The room is air conditioned, so getting a little more oxygen, getting a little more heat is not too bad. Okay, and you can see the white foam is coming out. And if I use some fire, for example, if I use imagine this is a stick, wooden stick which is glowing but not with flame, and if I put it inside, it will catch fire. Okay, that we can prove that this is indeed oxygen gas. You can do a similar one at home. Not with hydrogen peroxide, but by mixing vinegar and liquid soap and add sodium bicarbonate or baking soda into it. Okay? Alright, so I will make some space over here and keep this fellow on the floor. Now let's come back and see what has happened here. Can you see that the orange ice is gone? If you still don't see, I will focus the slide. No orange ice, right? And let's see what has happened to the green ice. See, the green ice is floating on its own melt. Can you see from a distance? Okay. So that means that the ice that I have dropped here is indeed D2O. Now you might say that I have cheated. I have added something to the water to make it heavy. Do you think that will work? Suppose I add salt or sugar to make the water heavy. Will it sink in water? In principle it can. But how many of you have studied Raoult's law? Depression of freezing point. You have studied that, right? Elevation of boiling point you have studied. So you know that if you add any solute to water or any solvent, it raises the boiling point, it lowers the temperature. So even if I have added something to water, it would have actually raised the melting point, and then in that case green ice would have melted after or before the orange ice. So the fact that it is melting at a high temperature clearly indicates that I have not cheated the experiment. It was real D2O. Okay, let's see what's the next one. A few things I will show on the video because those experiments are too dangerous to be done here. Okay, first a few things about chemical bonding, because just like this year is the International Year of the Periodic Table, 1916 or rather 2016, 3 years ago, was considered to be the centenary of the chemical bonding. Chemical bonds are being formed and broken for billions of years, right? Soon after the universe formed and it cooled down a little bit, chemical bonding had to happen, right? But then the understanding of chemical bonding, first time people really understood chemical bonding was in 1916 when G.M. Lewis, about whom we have started to read about from the high school days, he first showed that how chemical bonds can be formed by sharing of electron pairs. And of course, this is a cartoon diagram to indicate that when two orbitals are unequal sizes, like shaking hand with a small child or a baby, the physical bonding is weak. Okay. For example, if I take a nitrogen and a chlorine, or a nitrogen and an iodine, you don't have iodine here and nitrogen here. Iodine is big, nitrogen is small. So if I have an unequal size of the orbitals, the bond is very weak. For instance, the Ni bond strength is only 38, or roughly 40 kilocalories per mole. On the other hand, if the orbitals are of comparable sizes, the bond is strong and good handshake, and the bond is weak, and the bond is very strong, such as carbon fluorine, carbon oxygen, and so on. All right. Now there will be some fun for the younger participants. All right. Just have a little more patience. So I will now take not one but 3 Ni bonds. Okay, and I'll take nitrogen triiodide. You can imagine small nitrogen, 3 iodines linked to a small atom. All the bonds are very, very weak. And the molecule has so much of energy, it will explode when you provoke it, even with a feather. Okay, so let's watch this video. But remember, there will be a fourth or maybe fifth question. So watch and listen carefully. So what you see is Ni3 kept on filter paper.
When nitrogen triiodide, the dark-colored solid, is dry, it is very sensitive to touch or any vibration. Simply touching it with a feather causes it to explode or detonate. One detonation causes another to occur. One product of the reaction is violet iodine vapor. When nitrogen triiodide, the dark-colored solid, is dry, it is very sensitive to touch or any vibration. Simply touching it with a feather to explode or detonate. When nitrogen triiodide.
Okay, so you saw that it is so shock sensitive, you just have to touch it with a feather to make it explode. Alright, you remember that during Deepavali times, some of you might have used those crackers which you throw on the ground to make them burst. But here, it is just touching with a feather. So my question is, if this is so shock sensitive, how do you keep it on the filter paper? Okay, that's question number 5. Somebody must count the questions. Okay, you might have heard about hydrogen bonds. You must have read about hydrogen bonds, right, from high school grade. Hydrogen bonds are much weaker, less than 5 kilocalories per mole, okay, roughly. But hydrogen bonds play a very important role in chemistry and in biology, right? And everywhere else also. For example, the alpha helix structure, the protein secondary structure, the DNA double helical structure are all maintained by hydrogen bonding. Okay, hydrogen bonding is also responsible for this phenomenon that I showed you. That ice floats on water, right? Why does ice float on water? Not because of the density. Then the second question will be why is the density less? Okay, and that can be seen, for example, from this structure. The ice structure is sort of like a diamondoid structure, okay? Because every water molecule or every oxygen is surrounded by 4 hydrogens, 2 of its own and 2 through hydrogen bonding. So it's an open structure. There's a lot of open space here. But in liquid water, we will see on the left hand side, this is water which is being frozen, and you see it opens up quite a lot. So liquid water can have much more dense structure, so to speak, and can have every oxygen can have more hydrogen bonds. But when it freezes, when it gets frozen, it opens up, and that causes the volume to increase. Okay. Now we are going to do a simple experiment. Remember, some of you might have done this experiment. You take a bottle of water in a plastic container and keep it in the deep freezer. What happens? Bottle will expand because it's a plastic bottle. If it is a glass bottle, it will break. We are going to do an experiment. Again, it's very unsafe to do it here. We are going to do an experiment in which we will take an iron container, sort of like this, okay, put water and seal it completely, and then freeze it very quickly, and see what happens. It is too dangerous to do it here, so I will show you on the video. Before I start the sound, this is the iron container in the shape of a bomb. You will put cold water into it, seal it tightly, and keep in dry ice acetone mixture. Dry ice acetone mixture typically has a temperature of minus 78 degrees. Okay, so let's watch what happens.
The ice bomb illustrates the fact that the volume of ice is greater than the volume of an equal mass of liquid water. Some cold water is poured into a cast iron bomb, and a threaded plug is screwed into the bomb so that the bomb is tightly sealed.
You see it really well.
The bomb is then placed into a dry ice acetone slush, which is at negative 77 degrees Celsius, and will cause the water inside the bomb to freeze. A wooden box is placed over the top of the bomb and slush bath. It takes a short time for the water to freeze. When it does, the bomb explodes. Some of the dry ice acetone slush is blown onto the explosion shield. Little bits of the cast iron bomb are left. When the water freezes, tremendous pressure is produced. The pressure is enough to cause this cast iron bomb with more than 1/8 inch thick sides to burst.
So this experiment really tells you that even weak bonds, particularly when many of them combine together, that can pack a lot of energy. Okay? Because by the freezing process, all you are doing is to remove many water molecules from forming hydrogen bonds. So the expansion comes at the cost of removing many hydrogen bonds. So that packs in a lot of energy if you try to contain it in a small volume. So that was about weak bonds, Ni3 hydrogen bonds. What about strong bonds? Can you break strong bonds such as the bond in carbon dioxide? Carbon dioxide has a double bond which is very strong. Okay. But then, is there a way to break carbon-oxygen double bonds? Okay, and I'll show you an experiment which indicates that you can indeed break that. Okay, and this is a reaction between magnesium and carbon dioxide. Have you seen this form of carbon dioxide? Which is also called dry ice. Why is it called dry ice? Why is it called dry ice? Because it doesn't become liquid. It sublimes directly, like naphthalene, like camphor, which many of you have seen. Okay, you may not have seen dry ice, but dry ice is formed at minus 78 degrees centigrade and it sublimes directly. Okay. And you have to know the triple point temperature and pressure to understand why why water ice melts, but dry ice doesn't melt. Okay, so this experiment involves keeping some magnesium in the cavity of a dry ice and igniting it and covering with another block of dry ice.
Magnesium is placed in a cavity in a block of dry ice.
And then you ignite it.
The magnesium is ignited. And covered with another block of dry ice.
Now this burning magnesium has no air or oxygen around it because it's all covered with dry ice on both sides. But you see what happens.
Despite the absence of air, the magnesium continues to grow due to its reaction with carbon dioxide. Because of this reaction, carbon dioxide cannot be used to extinguish magnesium fires.
And we will now find out what happened inside, the chemistry part of it.
The reaction products are white magnesium oxide and black carbon.
So what burning magnesium has actually done is to extract oxygen out of carbon dioxide and reduce it to black carbon. You might think that this might solve the global warming problem, but then there's a catch. The catch is that magnesium metal does not occur free in the nature. Okay? Because it always comes as Mg2+. So to get magnesium metal, you have to put in that much of energy. And where will that energy come from? Unless you have a sustainable way of doing it. So this is not a way to reduce carbon dioxide, but this also tells you, it was stated in the video, that metal fires, including magnesium fires, cannot be extinguished by carbon dioxide because the metal will continue to burn in carbon dioxide. Okay. So be careful if there is a magnesium fire or a sodium metal fire and you only have a carbon dioxide extinguisher. Now nitrogen triple bond is even stronger. That is one strongest chemical bonds you can think of, 227 kilocalories per mole. Okay, and that's very high. Can you break it? Through lightning. Okay. Any other way? By bacteria. You are not talking about the most obvious way. Okay. Now I must apologize for this experiment which I normally do in real life, and all the setups have been done, but I realized to my horror that all the samples of this primary, secondary, and tertiary halides that I brought, they have all disappeared from this abundant tubes. This is the first time that everybody decided to give me a hard time. Okay, all the halides. So I cannot do this experiment. But let me ask you, this is something you have studied in high school. Suppose I say, which of them will react fastest in SN2 reaction? Primary. You know why, right? Which one will react fastest in SN1 reaction? Everybody knows that. But how do I show that to this group? Which experiment do I do to illustrate that the tertiary halide reacts fastest in SN1 reaction? Primary halide is the slowest. What experiment can I do to demonstrate? Add a strong base, it will not, adding a strong base is not SN1 type reaction conditions. Lucas test is for tertiary alcohols, not for halides. Woods reaction will require magnesium or sodium metal. I can't do that. Okay. Now let's look at it very cleanly. Okay. Suppose I react a bromide with a protic solvent, because under SN1 conditions I must use a polar protic solvent such as an alcohol. What are the reaction products? I get ROR dash plus HBr. Right? Very simple. Now, if I measure the rate of formation of HBr, I can find the rate of the reaction. Right? And how do I monitor H plus or Br minus? Br minus by silver ion and H plus by an indicator. Okay, so we have silver nitrate solution ready. We have universal indicator ready, but unfortunately we don't have the halides. But I have a backup option. Backup option is that I also have a video. So let me play the video. No, that is only one. That will not react. So that is not a good experiment. Okay, it says cannot open the file, but I will locate the file and then open it. Don't look at my directory structure. Okay. Butyl bromide isomers. Okay. So I will show you this on video. Let's say no to this. Do you see anything? I don't see anything happening. Okay, so let me open it with something else. Here and see how it goes. Okay. No, that's not the one. That's not the file we are looking at.
Most people are familiar with hydrogen peroxide solutions.
No, that's not the one. Okay, sorry about that. I will go back to the file and locate it again. Normally, it should open with VLC. Though for some reason it refuses to play, and unfortunately, then I will try once more with the real player, and if it works, fine. If it doesn't, finally it works. Okay, so what we have here are 3 jars with alcohol in it, and we are adding silver nitrate solution to that. And here I have N-butyl bromide, 2-butyl bromide, 2-bromobutane, that is secondary butyl bromide, and tertiary butyl bromide, which, as I said, have disappeared from my collection here. So what would happen is that if there is a reaction, HBr will be produced, and therefore the reaction which was fastest will produce a precipitate of silver bromide. Okay? So what they will do in this video is to first add the N-butyl bromide, which is something I would have done on this using this measuring cylinders. So you see that N-butyl bromide has been added and nothing happened, no precipitation, right? And therefore it is not reacting at any appreciable reaction rate. So now we will add the secondary and the tertiary halides together, and you will see the difference. Okay, so primary, secondary, and tertiary. You could see that the tertiary one reacted almost instantaneously, produced HBr, and the bromide formed, what did it form? It formed silver bromide. Okay. And with time, the secondary also starts to react, but very, very slowly. So when you say the primary doesn't react, it doesn't mean it doesn't react at all. It means that it reacts rather slowly. Okay? And you can see that the secondary has reacted in course of this time period, but the primary one has not reacted very much. Okay, so that is one part of the experiment. Let me also illustrate a second way of monitoring the reaction. I mentioned that you produce proton in course of the reaction. So in this case, what we are going to do is to I'm not sure why it refuses to play for the first time. Let me try again. Okay, this video refuses to play. Okay. Okay, so I will simply not waste too much more time, but this is just to indicate to you that if you want to do an experiment by which you want to show that which of these two is a better living group, you already know the answer, right? Which one is a better living group, bromide or chloride? Bromide is a better living group. Okay, larger the halogen, better its living group ability. So if you want to show this, you can do the same experiment, but what you do is you use an indicator by which you can see the formation of the proton. Okay. So I was planning to do all these experiments as I mentioned, but I could not do that. But that's all right. At least one experiment I could show you on the video. Okay. Okay. Now let me show a simple experiment on something. So the last few experiments that I'm going to show you will all involve color in one way or other. Okay. So the first experiment is about change of color with temperature. Okay. And to illustrate that, the chemistry is shown over there. If you make the silver salt of AgI42 minus, that's a yellow substance. But upon heating to 51 degrees, it turns yellow to orange. On the other hand, if you make a corresponding copper salt, that's red in color, but it becomes black at 67 degrees. Okay. I don't have the copper salt, but I have the silver salt. And what my students did is to paint a banana with this silver salt. Can we have the heat gun? Do we have the heat gun? You have to bring it from the lab, is it? Oh, it doesn't matter. You can send somebody to bring it. I can show you later. Okay, I can show this experiment later. So we are waiting for one of these heat guns, and we will warm it, and you will see that our banana is getting ripened. Okay, it will form more orange color. All right. So let's do it a little bit later. I think there are so many things to be brought from the lab. Somehow that has been missed out. So this is change of color with temperature. But colors can also change with solvent polarity. You all are familiar with polar and non-polar solvents, right? An example of a non-polar solvent? Non-polar. Water is the most polar. Benzene, petrol, kerosene, right? These are all non-polar solvents. Acetone is a sort of in between. So this phenomenon is called solvatochromism. That is change of color with solvent properties or solvent polarities. And I will show you. I'm not going to do this experiment, but I would show you a molecule which is called Ricar's dye. Okay, it's a Zwitter ionic compound, and that shows the largest solvent polarity dependent color change. For example, in methyl alcohol, ethyl alcohol, isopropyl alcohol, you know that they form a homologous series. They differ only by one CH2, but you see that this dye gives a very different color in methyl alcohol, ethyl alcohol, and isopropyl alcohol. Okay, and again between isopropyl alcohol and acetone, which are very similar molecules, very similar chemical structures. This color is sort of like an indigo color in isopropanol and green color in acetone. So if I have, for example, two bottles, unlabeled bottles, one having isopropanol, one having acetone, I can add a little bit of this dye and find out which one is which. If I have a drum of methyl alcohol and a drum of ethyl alcohol, I can find out which one is which by dissolving the dye and comparing the color. Okay. So this kind of a molecule can very easily tell you what is the solvent polarity that we are dealing with. Okay, incidentally, this picture was taken by one of my former students whose name was, not surprised, you will not be surprised, his name was Photon Rao. Okay. Very unusual name. So he did make use of different photonic behavior of these compounds. Okay, so the penultimate experiment I am going to do today would be on absorption and emission of light. Okay, when light passes through a medium, many things can happen. What are the possibilities? It may not get absorbed. Like I'm aiming this beam to the other wall and it is hitting there, that means between here and there it is not getting absorbed. Right? It can get scattered. And as you know, the scattering is a very important phenomenon. And setting sun looks red because of scattering, sky looks blue because of scattering, and so on. And third thing that can happen is that the light can get absorbed. Right? There are many substances which absorb light. For example, something that looks black implies that everything is getting absorbed. My t-shirt looks sort of like olive green because it absorbs all colors other than green. Now, when a molecule or a material absorbs light, two things can happen. Broadly speaking, I'm simplifying a few chemical and physical principles, but that is probably okay. An excited state can either lose the energy by heat, when nothing happens to you, you won't see anything, or it can lose the energy in the form of light. What is that phenomenon called? Fluorescence. Okay, so I will use a few simple experiments to illustrate these principles. Okay, and I have all the lights off, please. I will switch off. I will first show the principle here. For instance, I have an incident radiation. How many of you have studied Beer's law? Oh, many of you. Okay. Beer-Lambert's law. Okay. So when light passes through a medium where the light intensity gets absorbed, okay, the thickness of the arrow indicates that the number of photons here is more, then this I is less than I0. And this is Lambert-Beer's law. Log I0 by I is what is called an absorbance, which is equal to epsilon, which is the property of the molecule or material, also called the extinction coefficient, concentration, and length. And then when it gets absorbed, again many things can happen. One of them is fluorescence, which is often read or measured perpendicular to the path of this one. And in this case, the intensity of the transmitted radiation is less, the wavelength of the emitted radiation is longer than that of the incident radiation. Okay, and that can be illustrated by this principle. Okay, that comes a little bit later. Can I have the lights off, please? All lights, including the stage lights. Now let me show you a picture which I probably shouldn't show here because of two reasons. How many of you can recognize this? This is a very popular drink, an alcoholic drink, and since we are in a state where there is complete prohibition, and most of you have not reached the drinking age anyway, we will remove the organic solvent. Alright. So this is what is called a gin and tonic. Alright. Now the question is, so let's remove the gin part. Okay, this is tonic water, this is harmless. But then the question is, what is meant by tonic water? Do any of you know what is tonic water? Okay, when the British came to India and Southeast Asia, like now we have malaria, there used to be many more cases of malaria at that time. Okay, and the only drug available at that time was quinine. So they used to add small amounts of quinine to water and drink it every day. Okay, and that they call tonic water. And of course it tasted bitter, because quinine is very bitter. And therefore they added something else to make it more interesting. Alright, so that is the history of gin and tonic. But then now we have removed the gin, only tonic water remains. There it is. Okay? Alright. Now what this has to do with absorption of light or emission of light? You know? Because it has quinine, which is a fluorescent molecule. Okay? So what I'm going to do is to take two glasses. This is an experiment that can be safely done in a state even with prohibition, because there is no alcohol here. Okay? So I put Sprite in one of the glasses, which does not have any quinine. Nice glass, exactly 50 ml size. But of course, I'm not going to drink any of these things. And this is tonic water. This, again, I will have a question about this to you, which has small amounts of quinine in it. This is also carbonated drink. Okay. This is more than 250, so not all of it will fit in there. And now what I'm going to do is I need to make some space available there. Now I'm going to switch up the light. Okay. Now one of them is, oh my god, I forgot which one is tonic, which one is Sprite. How do I find out? How do I find that out? By the fluorescent property, let's see. Which one is fluorescent? The one on your right. Okay? The one on your left is showing no fluorescence because it is bright and it has got no quinine. On the other hand, this glass came from the tonic water, you can see, it is showing beautiful fluorescent blue color. Okay? And that proves that there's quinine and therefore this should be the tonic water. And you can see that here, I hold the light in the same way, there is absolutely no fluorescence. There is a little bit of reflection of this UV lamp, UV light, but no fluorescence. But here you see beautiful fluorescence. Okay? So that tells you that you can detect small amounts of quinine by a simple experiment. Okay, so that's all the reason I brought up the story about this tonic with something else. Okay, of course, if I smell it, I can distinguish the two because Sprite has a very different smell than the tonic water. Okay, so the tonic water, if you want to see the details, it has got, you know, again, I would like to tell you that when you read the labels, you learn a lot more about the chemistry because it says it has got an acidity regulator 330, preservative 211, and if you look at the E numbers, 211 is nothing but sodium benzoate, which is often used as a preservative. 330 acidity regulator, in this particular case, it is citric acid, okay, or citric acid, which is found in lemon. Okay, now I'm going to show you one more experiment about emission of light, and that is using visible light. You know, this is the visible spectrum, visible part of the electromagnetic spectrum. 400 nanometer is violet, 700 is red. This is higher energy, this is lower energy. So I'm going to show you an experiment involving absorption of green light and emission of orange yellow light. But as I mentioned, that when you shine light through a system, there can be no absorption, there can be scattering, and there can be absorption followed by emission. So to illustrate that, I'm going to fill water in these 3 measuring cylinders. Here, let me make sure I have water here. Are you getting bored? Are you sure? I can only tell you that the last experiment is the most interesting experiment. If you want to leave, I can stop now itself, but I have not done the last experiment. Okay, alright. So I have water in these 3 sample measuring cylinders, and I deliberately will keep a black background here, but I will change it to white also if necessary. And this one, I am not adding anything. In the next one, I will add a few milligrams of milk powder. Okay. That's enough, that should be enough. Okay, because this milk powder will not dissolve completely and will make the light scatter. Okay. What is the third one? I'm going to use again this very expensive material. Okay, and this is nothing but, in case it is too dark, this is nothing but a 20 rupee highlighter, pink color. Now this usually has a dye known as rhodamine. Okay, so I'm going to add a little bit of this color to the water. Again, you see these experiments are very straightforward experiments. Okay, and mix it up. And perhaps you can see when I take a white background that it is slightly pink in color. Okay, now that's why I have this pink object earlier in the earlier slide. Okay, so this on your left will not show any absorption. This will show scattering because I have got some milk particles in it. Whereas the last one is rhodamine, which will absorb only green light and will emit orange, yellow. But I'm going to do the experiment with both green laser and with red laser, because in the last case, green will show yellow color, red will not show anything, because red is at the other end of the spectrum and that will not be absorbed by rhodamine. So the first one, no absorption, right? There may be a little bit of scattering, but that may be because of the suspended particles. Neither from green nor from red. This is milk suspended in water. You see the scattered light? You see the scattered light. And you see the scattered light with green as well. Okay? It's the milk, I think the milk powder has become old, so it has not dissolved to the extent it was supposed to dissolve. Okay. So this is showing scattering, this is also showing scattering. Now the fun part, this is rhodamine, right? It will not absorb red light because it absorbs green and emits orange, yellow. Both have higher energy than red light. Okay. So the red light, when I shine through it, you see some scattering because of the large particle size, but you see no change in the color, right? Now the last part of the experiment, let's see if it works. I shine green light, and what do I see? I see orange yellow, right? So that is clearly because of absorption and emission of a different wavelength. Okay, and this is basically the principle of fluorescence, or also known as photoluminescence. Okay, I can normally lift it up here. Let me make the room little darker and show it to you again. Okay, you can see the color completely changes because of this change in wavelength of light. Okay, all right. So the last experiment I'm going to show you is conversion of not light into light, but chemical energy into light. Okay, and that principle is basically what would be called chemiluminescence. You must have seen fireflies after the rainy season, particularly in the rural areas where there are still some bushes and forest areas, not in the Ahmedabad town or in Gandhinagar town. But this is a general principle of phenomenon known as chemiluminescence. Okay. So what we are going to do in this experiment today is the following. We are going to use hydrogen peroxide as our chemical fuel. Okay? And react it with something called oxalic chloride. It will produce a very strained molecule such as this, which is nothing. If you look at it closely, if you break it along these lines, what do you find? You get 2 carbon dioxide. And that's what happens when it decomposes. It's very unstable. But because it has a lot of energy, when it decomposes, it produces 1 carbon dioxide, which is a normal carbon dioxide. The other carbon dioxide is electronically excited. You know about atomic spectra, right? Excitation of an electron from, let's say, 1s orbital, 2s orbital, when you study hydrogen atom, the classical Bohr theory. So, similarly, molecules can also have molecular orbitals and electrons can get excited from their HOMO to their LUMO. But in this case, carbon dioxide is not a fluorescent molecule. So the electronically excited carbon dioxide, when it comes back to the ground state, it doesn't show fluorescence. Okay, it loses the energy as heat, so that's not exciting. But what we are going to do is to add a sensitizer or a fluorescent molecule which will trap the energy from the carbon dioxide and itself will get electronically excited. And because these are fluorescent molecules, when they come back to the ground state, they will emit light. So what we will achieve is conversion of this chemical energy directly into light without heat. When in heat, let's say coal or a tungsten filament, ultimately it is electrical energy or thermal energy that goes to light energy indirectly. But in this case, chemical energy will be converted directly into light. And today I am going to show you 4 different dyes, 9,10 diphenyl anthracene, which will give you a color roughly of this type. Rubrene will show in orange color, perylene will show a sky blue color, and tetrazene will show a green color. Okay, so give me a minute or 2 to set things up. One more conical flask. So I need to measure some amounts of these dyes into the conical flasks. Okay, we'll come back to that. So from your left, I'm going to pour some diphenyl anthracene on the first one on your left. I must see what I'm doing. Okay, that will give you a sky blue color, not sky blue, that will give you a different blue color, violet blue color. The second one is green. Again, these are materials that have been provided by mud sigma rate, so I must once more hang them. So that is green, that will give you an orange color, very similar to the fluorescence color that you have seen a little while ago. The third one from your left is Beryllium. I should be able to read the labels also. Okay, third one is beryllium. The fourth one is tetrazine, which looks like two naphthalenes connected together, but it's very expensive. Okay, in the sense that 100 milligrams cost about 12,000 rupees. So I'm going to use probably 400 or 500 rupees worth of tetrazine in this experiment. Okay. All right, but this is thanks to the chemical industry which has supported this experiment. So I'm going to add some dichloromethane, CH2Cl2, to each of them to dissolve these materials. Okay. Now, if I keep this bottle of dichloromethane outside, it will disappear. You know why? Why will it disappear? Because outside temperature is above its boiling point. Okay, so you can guess the boiling point. Okay, so we are all set to do the next experiment. And here I have oxalyl chloride, and here I have hydrogen peroxide. And of course, this tonic water and Sprite are not needed anymore. So I put one dropper here, and one dropper I will get with the oxalyl chloride. Okay, and let me also remove the clutter a little bit so that I can do things peacefully. Okay, are we ready? So, one of you can come here and hold the torch just in case I need some light. Because I'm going to switch off all the lights. Can you close the door, please? So first I will add the oxalyl chloride. Okay, good. Lights off. Okay, you can switch off the light, torchlight also. Okay. So now we get light out of chemical energy. Alright. So as I mentioned, this is, oh, but this is not fire, this is light. Okay. Now I'm going to do one thing. I'm going to mix some orange color into the blue. Because orange and blue are complementary colors. So this will become orange, then white, then blue again. Let's see if it works. Okay. This is white and then blue again. Let's do the titration once more. Orange, white, and blue. Okay. And this experiment can be very easily demonstrated. Again, you can see the difference in the color by mixing in different proportions of the orange and the blue. So the orange light will disappear quite rapidly. So let's do the remaining two colors also by taking again oxalyl chloride. And let me get rid of this oxalyl chloride because it's pretty harmful chemical if not used carefully. And add hydrogen peroxide to each of them. There is enough light here, I can see what I'm doing. And I'm going to add hydrogen peroxide, so this will be sky blue and this will be green. As promised, you get all the four colors that I had shown earlier. Okay? So the one that you see on your left is the sky blue from beryllium. The one that you see on your right is the green from tetrazine. Tetrazine is a very reactive molecule, so that color will not remain for too long. Okay, but this sky blue blue color that you see here, and in fact I can see who she is by this color. Okay, so this is enough, and you can also see the speaker's face. Okay, because this light is pretty intense, particularly when the room is darkened like it is now. But you will see that this color will remain for quite some time, but this green color will disappear. Okay, again, this may look like magic, but once you know the chemistry behind it, it is very straightforward to understand. In this case, of course, it is not just chemistry, but there is a lot of photophysics that you will have to learn. Okay, I have used up all the orange material, but the orange material also loses color quite rapidly because root green is somewhat reactive material. Okay, so let's go back to the slide. So you have seen that all the four colors were produced. One experiment that I did not or could not do earlier, I think now we have got the. Now we can have the lights on, please. Not the stage light, but the room lights. Yeah, here you see the banana, and I'm going to heat it up and show that this will become orange. Maybe from a distance you may not be able to see it, but perhaps you can still see it. Do you see a change in color? I think some of the coating has come off, so you may not be able to see it very clearly, but this color change is completely improved. Completely reversible because it will go back to the lemon yellow color again when the temperature drops below 51 degrees centigrade, and I can do that by waving it like this. Okay, so that is more or less the end of my experiments, but I'd like to just I'm not done yet. I'm not done yet because we have only seen the experiments and some of the principles we have seen. But there is time for little more exchange of information. Okay, and can I take a few more minutes, maybe 10 minutes? Is that okay? Because I also would like you to take home, take some messages back home or to your hostel or wherever you are. The first question. This was my first question. What is this? This reactor, I gave you so many hints. I said you have studied it in high school. I said, what is the strongest bond? N triple bond. How do you break it? You said everything except one. That you have studied in your high school. Haber's process. Okay. This, in fact, is a ammonia reactor kept outside the BASF factory in Germany, in a place called Ludwigshafen. It's about a 30 feet long reactor, and that was initially made by Haber and Bosch. And this was used for 55 years and produced 800 million metric tons, close to a million metric ton of ammonia. Okay, all right. Now let's see who can identify this gentleman. Linus Pauling, correct. So Linus Pauling has a very unique distinction that he is the only one who got two unshared Nobel Prizes. One in chemistry, one in peace. That's right. I have a short video on the life of Linus Pauling which I thought I will play. It's about 7.5 minutes. Short. I'm sure that many of you watch much longer videos on your mobile. Okay, so this video I hope. Yes.
I like to understand the world. I like to learn about new ideas. I like to think about problems, look at them in different ways, and finally get an answer to it.
Linus Pauling was convinced that understanding structure was the key to unlocking some of the mysteries of the universe.
To understand the human body, we must know its structure in terms of the cells that make it up. If we want to understand cells, we must know their structure in terms of molecules. If we want to understand molecules, we must know their structure in terms of atoms. And to understand atoms, we must know their structure in terms of electrons and nuclei. To understand nuclei, as the physicists are trying to do now, we must learn their structure in terms of protons and neutrons.
Linus Pauling wrote, "The study of the physical world, and I would say the biological world too, is a search for structure and not a search for substance." As a small boy, Pauling's interest in science was awakened as he played in the back of his father's drugstore in Condon, Oregon. His fascination with structure also began in his childhood when he collected and studied the structure of rocks and minerals. Pauling was introduced to chemistry by a boyhood friend.
And one day when I was 13 years old, he said to me, "Would you like to see some chemical experiments?" And I said, "Yes, I would." We went into his house up to the second floor where he had his little bedroom, and he carried out about 3 experiments, which really astounded me. They pleased me immensely.
Pauling later said that he decided to be a chemist right then and there. He went to Oregon Agricultural College, now Oregon State University, where he excelled in every science and math class offered. He went on to study and then to join the faculty at the California Institute of Technology in Pasadena, California, where he was to remain for more than 40 years. After his 1925 graduation from Caltech, Pauling studied with European physicists who were developing the new theories of quantum mechanics. In 1931, he applied this training in physics to clarify the nature of the chemical bond. He recalled his discovery.
I was so excited and happy. I think I stayed up all night writing out, solving the equations, which were so simple that I could solve them in a few minutes. Solve one equation and get the answer, and solve another equation about the structure of octahedral complexes, such as the ferrocyanide ion and potassium ferrocyanide. And it didn't take me long to write a long paper about the nature of the chemical bond. That was a great experience.
Pauling's work on the nature of the chemical bond transformed the way chemists work and think. In the spring of 1948, Pauling caught cold and had to stay in bed for a few days. Bored with detective and science fiction stories, he began to ponder the structure of proteins.
I took a sheet of paper and sketched the atoms with the bonds between them, and then folded the paper to bend one bond at the right angle, what I thought it should be relative to the other, and kept doing this, making a helix, until I could form hydrogen bonds between one turn of the helix and the next turn of the helix. And it only took a few hours of doing that to discover the alpha helix.
The alpha helix was a breakthrough discovery in understanding the structure of proteins. Pauling was a gifted teacher, able to simplify in ways that made his ideas accessible even to the general public.
Know a good bit about the structure of simple molecules. Now the time has come when we can learn something about the structure of complicated molecules too. The human body contains many kinds of molecules, such as the water molecule, H2O, with only 3 atoms in it. Also, many very complicated molecules, among which are the proteins. Proteins are very important substances. I think that a human being may well have in his body as many as 100,000 different kinds of proteins.
Pauling's work with the large molecules of proteins and hemoglobin led to his idea that sickle cell anemia was a molecular disease. This concept opened the way for the whole field of molecular biology.
From what I know of the properties of these patients, I believe that this
is a disease of the molecule, and that if we look at the blood of these patients, we shall find that the hemoglobin molecules are different from those of other people.
Pauling went on to prove that sickle cell anemia is indeed caused by an abnormality of hemoglobin molecules in red blood cells. In 1954, Pauling won the Nobel Prize for Chemistry. The prize was given for his work on the nature of the chemical bond. The first time the Nobel Committee had honored a scientist for the body of his work rather than for a specific discovery. Pauling's increasing interest in biochemistry led him to investigate mental disorders and the process of aging. He developed the concept of orthomolecular medicine and began a 20-year crusade on behalf of the molecular benefits of large quantities of vitamin C. In 1987, Pauling modestly summed up the secret of his astonishing career.
You aren't going to have good ideas unless you have lots of ideas and some sort of principle of selection.
A biographer wrote, Pauling's audacity was coupled with deep chemical intuition, and his overall ability to identify sound ideas and reject unsound ones was remarkable. Perhaps more than that of any other modern scientist, Pauling's work spanned all the levels of physical reality, from the submicroscopic world of elementary particles to the macroscopic world of living organisms. Pauling's genius was in his vast understanding of the nature of the universe and in his inspired guesses about how the universe works.
I hope you have enjoyed the video, but there are a couple of things that I would like to point out. One is that he mentioned that he worked on the structure of alpha helix for 11 years. He was not successful. And eventually he solved it when he was in hospital bed. So the message that comes out of it is that even if today you are unsuccessful but working on an important problem, don't give up. Okay? Don't give up even when you are in a difficult situation similar to this. Okay? Pauling obviously did not. Okay? The other thing is Pauling said towards the end is that when you should have lots of ideas. Okay? And a principle of selection by which you throw out the weak ideas and work on the strong ideas. If you have only one idea which is not very strong, that will not take you very far. So you must have lots of ideas. Start writing down all your ideas, thoughts that come to you in a notebook, and you will find out a month later, maybe 6 months later, that many of your ideas that you wrote down today, 6 months later, they do not appear very strong ideas. So you do not have to pursue them. With that, I would like to conclude my talk, but again, I would like to point out that, again, this is something that comes out from when you read about many people who have become successful, is that always keep your eyes open. And I had a line that it said when sleeping. Then the important thing is that you might have read the statement by Pasteur which says, chance favors the prepared mind. Because nature throws different kinds of problems at you all the time. But unless your mind is prepared, unless your eyes are open, you may simply ignore many important things and simply pass it off to somebody else to take advantage of it or exploit this. So always keep your eyes open and be prepared for taking up important problems. So with this, I thought I will conclude, but then this elephant comes back again. You know why? How many of you have heard the periodic table song? Only one, two, only a few. Well, as I said, this is the International Year of the Periodic Table. We cannot not play the periodic table song. Interestingly, this song, you can actually sing and dance. This song was composed by a physicist, a mathematician from Harvard University. Okay, his name is Tom Lehrer. And then subsequently an animation has been given to this, but we will play the song and then I will stop. Okay, here it says that Tom Lehrer, mathematics professor at Harvard, and he composed it sometime around 1955, okay, on the elements known at that time. Okay, so let's listen to the song. There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, and ruthenium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and actinium, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, and terbium, actinium, rubidium, and boron, gadolinium, niobium, and iridium, and strontium, and silicon, and silver, and samarium, and bismuth, chromium, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercury, and molybdenum, and magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, and plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, and mercurium, and also mendelevium, titanium, nobelium, and argon, plutonium, and radium, and rhodium, and chlorine, cobalt, copper, tungsten, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered. Okay, friends, that's the end. But I do hope that I have been able to show you that by doing very simple experiments, you can learn many principles of chemistry. And most of you are studying chemistry anyway, right? But I think the message that you get from the experiments that I have shown you today is that you can also take these things to younger people, maybe to school children, and add your own imagination, add your own understanding of chemistry to design new experiments which can be done with simple household chemicals, and get people to be interested in chemistry. Let the common man know that chemistry does so much for you. Okay, that's something that in our, not just in the Indian context, in the global context, people somehow are afraid of chemistry. They think that chemists are the ones who make all these bad chemicals and things like that. Okay, and these days there is a lot of talk about chemical-free organic produce. Okay, so I often joke that the only chemical-free item that you can have is real vacuum. That's the one space that you have which is completely chemical-free. There's nothing in the world that is chemical-free. But people have different sort of perception about chemistry. And I think that you have the responsibility as chemistry students, as science students, to change this perception. So let's all work towards that. But before I finally end, I would like to ask the team that supported me directly and indirectly. Please come forward. All of you, who have done a lot of background work and helped me in not only getting these chemicals. Yeah, please come. So please give a big applause to all the help that's required to get the chemistry going on the table over here. So thank you very much. Thank you all. But what about the answer to the questions? Remember this Ni3 that I mentioned. How do you put it on the filter paper if it is so shock sensitive? What's your answer? You know what happens during Deepavali time if it rains? If your patakas go wet, they don't work. They don't explode, right? So, in this case, when Ni3 is made, it is made as a water suspension and put it on the filter paper. And then when it is dry, you come back with a feather and explore. Okay. Did I ask any other question? Which is unanswered? No. Okay. But you can ask me a question if you want. No. If you don't add soap, you don't get the lather. It's only because of the soap that we force it to form bubbles. Oh, I promised you that I'll tell you a joke. Ah, yes. Two chemists. Can I take 2 more minutes? They want to hear the joke. Two chemists go to a restaurant. Okay, and they said, we want to have a drink. Not anything of this kind. So they were both chemists. So they said, one of them said, "Can I have some H2O?" The waiter says, "Yes, you can." Second guy says, "I would also like to have some H2O too." Only one of them survived. You know what? But then I have a little continuation of the story. The second guy was given H2O too, but he said, "I would like to have my H2O too with a pinch of salt." And then the waiter said, "What kind?" He said, "Iodized salt." And then he added the iodized salt, and H2O became H2O, and which he could drink happily. And you have seen that chemistry, right? Now this is only a joke. Don't try to do this thing by taking H2O2 and adding iodized salt and then drink it. Okay? You may still get burns in your mouth. So don't try to do any of these experiments unless you are sure of what you are doing, and never touch anything from this working place. And never put anything in your mouth from what you have done. I can say that, oh, this is 7-Up or whatever that is, tonic water. I can drink this, but once you have done experiments, never touch anything, for drinking or eating. So these two things have to be very clearly understood. That chemistry lab is chemistry lab. You have to respect chemicals. If you respect chemicals, chemicals will also respect. Thank you very much.
Dear sir, thank you so much for your inspiring words. With this lecture, you really have taught us some amazing lessons. That chemistry is much more than chemicals. There is so much more to achieve and so much more to gain. So please give him a huge round of applause.
I'd like to call Professor Shivpri on stage to present the memento.
Professor Maitra doesn't mind, I will also call 2 of his other students, Vijay and Chandra, to come to the stage. We are all students of Professor Maitra, and you can see that we are doing well because we had teachers like him. So.
Okay. Oh, okay. Thank you. Thank you. Thank you.
I'd like to add one word to him here. And he is the best teacher ever I had at IISc Bangalore. And he inspired a lot by teaching physical organic chemistry to us. And I'm a little bit continuing that inspiration here. Thank you.